Hello and welcome to another video of Programming for Data Analytics Part 2. Today we're going to be introducing the scikit-learn library, which is a machine learning library. And I'm just going to give you a very basic overview of it. And then the following videos will focus on different algorithms that you can do in the library, amongst other things. So first, let's kind of explain why we're bringing machine learning into the equation. So far, between the 621 learning Python and 622's beginning, which we were talking about web scraping and all that web analytics process, ultimately, what you have been doing is collecting data, right? So you're collecting data. So we've done that. We've done that either through web scraping, or you have the data, you load it in with Python. So you use Python to kind of move things around, but ultimately you want to get that data. From there, you're sort of the next major step when you're doing your analytics is you want to process the data, right? And this processing can be multiple steps. Like you got pre-processing, where you're organizing and cleaning up the data, and then you are organizing, like initial pre-processing can just be removing bad data, trying to like insert this into like a CSV or like a spreadsheet that you can then read into Python. There's a lot of things, but ultimately you play with the data till you get it into a position where it's ready to be analyzed. And so you process it. Once you kind of have it ready to be analyzed, then the analysis is going to be sort of done as a two-path scenario. On one side, you want to look at the data yourself and you want to make decisions on that, right? So on one end, like a human, so you look at the data. However, this, depending on the kind of data that you're working with, might not be very practical to do, particularly if you're working with like large amounts of data. It's more easy when it's like always just a table or a little spreadsheet, things like that. Then yes, that's not too much of an issue. The real issue comes when you're looking at like massive amounts of data, and a real human can't really look at that. So there you kind of have to step aside from that and just sort of look at a small piece of the data to kind of see what you're working with. And then when you're ready to kind of process the entire data, you need to feed it to a machine. And let the AI, artificial intelligence, which is your machine, do what you can't do or would take you a very long time to do. And what kind of things are you trying to look for when you're doing this? Well, first of all, you have to develop or to figure out what performance, if your data is like finance or something, we want to see like, well, I want to know some performance indicators, right? Or if your data is medical, you have to decide, well, I want to see certain patterns in the data that indicate certain flags for a certain disease. So you have to make these metrics, right? So ultimately what you're doing is you're formulating your metrics here. And you want to have a way of deciding whether something is good or something is bad. So in those cases, we're talking about something like a binary classification, or if it's something within a scale. So like not necessarily good and bad, but like within some sort of line or curve or whatever it is. So for example, good and bad can be like whether somebody is positive or negative for COVID-19 based on symptoms. That is something that is binary. You could also have multi-classification, so it doesn't have to be binary. It could be like within like 5 groups. So like, for example, personality types, right? So there's like a couple of different personality types, but there's like, it's a fixed amount that they'll have based on like their books for this stuff. And so you read certain things about a person and then fit them into a specific category. But those are limited number of categories and are predefined from the beginning. So that's still classification. And then your other sort of alternative is more of like kind of like regression, where you're trying to predict something based on something else within a unbound sort of line, okay? Curve, whatever that might be. So ultimately, there's a lot of ways to do this, but one of the powerful ways that you can do with Python and with programming in general is you can use machine learning. So this is where your machine learning is going to come into play. So all this stuff kind of happens here, okay? And then once you get out of that, then you get your results and you formulate your strategy based on that. All right. So this is where you review what you get, whether it may be from a person or from a machine, and then make the decisions. And you could make another machine make a decision potentially. So like if this is connected to like a market, you could make this place a buy or sell order automatically. So as an example for that, like your data collection could be Twitter API. This could be a Python script. The second step, so let's say this is a Twitter API. Processing it is potentially translating what the Twitter API really represents. So actually, downloading, extracting certain keywords that you want from certain people's tweets and things like that. Maybe even performing some sort of sentiment analysis on a tweet. So what would that be like? Whether somebody tweets about a stock in a positive way or in a negative way. To be able to understand whether it's a positive or negative tweet, you have to look at the keywords in it and see if those are positive words or negative words. So like, screw this stock, that's probably negative, versus like, I just bought 10 million orders of the stock or something. That could be a positive thing. So you have to understand whether something is good or bad, or if there's emojis, things like that. So there's your sentiment analysis, right? So the point is you're doing some processing either here to prepare it for sentiment analysis, or you do the sentiment analysis in this step. Ultimately, you feed those rules or the results of things like that to your model, to your machine learning model, which is going to decide whether you should buy or sell the stock. So there's a binary classification, buy or sell, based on things like sentiment analysis inputs, amongst other inputs. Okay, and then your formulated strategy in this case is literally going to be just do a purchase order or do a sell, short the stock or go long on the stock or something, puts or options, whatever. So this could all be automated potentially, but it doesn't have to be, okay? But really what we are interested in right now is this, okay? So when it comes to machine learning and Python, there's a couple of steps that I want to go over. So first, when you think about machine learning, what you need to train someone to do something, whether it's, I wouldn't say humans, because humans work different sometimes, but at least machines. When you're trying to train someone to do something, what you want to do is you want to provide them examples of how to do something right, so that they can look at those examples, learn from those, and then when faced with a new situation similar to their previous experience, they can use that previous experience to apply it to the new situation. Or if they run into an experience that is identical to a previous situation, then they just perform what they know, right? So like think about a pilot training. So a pilot is training to fly a plane. They're going to go in a simulator and they're going to experience all the things that you would experience when you're flying a plane. Taking off from a runway, landing from a runway, but also they're going to do some emergency procedures, right? Like, emergency landing, or we just lost an engine or something. Like they're gonna go over those kind of scenarios so that if they ever face the real life situation, it's either going to be identical to the failure that they already practiced with, in which case they can reference that knowledge and just apply one-to-one, or they might have some sort of new failure, but it's similar to what they might have had in training, so they can apply that previous training experience and approach this problem using that, versus like trying to go from scratch. So that's kind of the same way that you train a machine. You train it with as much knowledge as you can, so that once a new situation arises, it can look at that history of knowledge and either find an exact match, or make it infer from the given training data the new potential data that's coming in. Okay, so to do that, you have to train the machine, and the way you train the machine is more than just like think about the pilot for a second. You don't just sit the pilot in the simulator. I don't just show you things in class. I make you actually do work, right? I make you try out the Twitter API. In 621, I made you take a test. In this class, I make you make a project. So that in that class, right? So I do these evaluations to see whether or not the training was successful, whether or not you learned this programming knowledge, right? That concept is the idea of testing and validating somebody's training before you throw them out there. You want to not just say, well, I gave him all the training I could, but you also want to evaluate the training and see whether it's effective or not, so that you can be confident to a certain degree when you feed new data that it should, in theory, based on like, testing experience, it should work out. So like, if I say I'm going to teach you how loops work in Python, and I showed you loops, and then I give you assignments on loops, and I give you an exam on loops, and I give you a massive project on loops, then I want to say that you know loops at that point. So if at any point in the future you get a loop problem, then you can use that previous knowledge, and I can use the confidence that you succeeded when I evaluated that previous knowledge, that you actually will know how to do a loop, right? That's much better than saying, oh, let me just train you on loops and then throw you out there and then like say, oh, this person's an expert on loops. I've never actually tested them on it, but I told them what loops were and they're an expert on it. That's, of course, kind of not as confident per se. Or you might sound that confident, but really, are you good at loops? You ever tested with a loop? Have you ever been in the scenario where you saw a loop that was slightly different than what you learned? And so we also want to apply that knowledge to the AI or to the machine learning model. We want to say, okay, I'm going to train you on this piece of data that I know what the answer is to. So I'll tell you what the data is and what the answer to that data is. But rather than feeding you with all the training data that I have, I'm going to split that. I'm going to split it like this. So suppose that I'm trying to train a machine to understand a color or a shape. Let's do a shape. So I feed you a bunch of shapes, and they might be all slightly different. So I'm feeding you just a bunch of triangles. They all look kind of different, and they are, for the most part. I mean, they all look like triangles, but they're not exactly the exact same dimensions and shape. As you can see, I can't draw a perfect triangle, so obviously they're not perfect. And all of these, I'm feeding you and telling you that those are triangles, right? So this is your input, and this is what the output should be. And yeah, just all triangles, okay? But here's the thing. If I give you all my triangles, what am I going to use to test you with? I'm going to have to come up with new examples. But what if I don't have any new examples? These are all the triangles that I have. What I want to do is I want to take a small subset of this. I'm going to split my data or my training data into two pieces. In fact, I can actually split it into three, but let's start out with two. I'm going to split it into two, and I'm going to call this my training data. And I'm going to use this or call this my testing data. So I'm going to let you do all you want with this part to train. And repeat it as many times as you want and do whatever. But once I'm like, okay, I think you're good enough. I think you're ready. You're ready for this now. Then I'm going to feed you the testing data, which I also know is a triangle. And then I can use this to evaluate, because you've never seen this data. You've never seen the test data. You didn't train on it. So I can use that to test this, and I know what the answer is. I can quickly do those tests automated. I'm going to feed you that and see if you detected triangles. And if you detected all these three are triangles, then I can say that the training succeeded. If you detect two and one not, or let's say you detect two wrong and one yes, then I can say that the training failed. It was not good training because you did not get that. So, if you get 30%, 33% accuracy, then I'm going to say the training failed. If you get 66, well, it's a small subset of number of things to test on you, 3 things, but 66 is pretty bad. Ideally, you want to get something above 80 before you start even considering it as being okay. Because really, if you get anything less than 50, then you manage to somehow lower your odds. Like if there are only 2 choices, triangle or circle, and you develop an algorithm and it's literally getting 30% of the time wrong, then all you really got to do at that point is literally flip the answer of your algorithm, and you just went from 30% to literally 70%. Because if you get more than half wrong, then you might as well just flip a coin and you would have gotten better luck, right? Anything less than 50 is literally you could have just flipped a coin and done better, because with flipping a coin you got 50-50 chance. So you shouldn't even ever get less than that. So that's really red flag that your algorithm messed up. So because we basically think of 50 as the worst case scenario, really, then 80% is not as good as it sounds, because it's almost it's better than half, but it's not saying much. Obviously, we want something like 96%, 97%, even 91%. I would be okay, we're getting somewhere. If you can detect whether something is a triangle or a circle 90% of the time, then it becomes actually usable. And so you don't want to leave too much of test data and too little training data, because then you are not going to train effectively. But you don't want to leave too little test data that you don't really get to evaluate how good your program is doing. But this can go further. When it comes to reproducible research and publication of your research in general, you don't want to be caught finessing your data set. Now, what does that mean? When you're training a model for machine learning, and you do this whole training and test idea, what ends up happening is you might do what is known as overfitting. And it might have been mentioned in the previous video, but I wanted to bring it up again. So overfitting means that you train too far to the point that it becomes really good. So you're getting 100% accuracy with your training stuff. And if your test data is close enough to your training, you might even get 100% accuracy there. But if you see something that is a little bit too different from this, it's just going to completely fail. Because it really went so far as to say, well, what's really making this a triangle is not the general shape, but maybe the thickness of the line, or something the little curves at the bottom. Or what I'm saying, this thing, at the bottom. You see this thing right here, or this thing. It's overfitting to even those things. That's not good too. So how do we make sure that we're not in that kind of situation? Well, sometimes they'll split this into a third piece. So they'll actually leave a little bit more of the data set, maybe a couple of more triangles in here, and I really should have at least 2 more there. So maybe they leave something like this. And then this piece they call the validation. And so the way this should work is you train on your training data, you occasionally test on your test data set. If that's not good enough, you go back and keep updating, improving the training until your test is really, really good. Then once you're truly convinced that you develop a good algorithm, only then and not before, you go and test on the validation data set. And that one is a one-timer. If you do good on it, you can say that you did a good job. If you do bad on it, you cannot go back and start updating your training data to see if you can get around, and if you tweak it around enough so that both your test and validation are good. That's finessing your data, because you're not being honest at that point. You're just trying to make it work for this special case, and then it's probably not going to generalize to the rest of the possible cases out in the real world. So that's more of from a publication standpoint. If you're trying to publish and say, well, I did this and here's my validation accuracy, then it shows that your algorithm is slightly better. Okay, but that's just kind of like a quick summary of that, of how they split those systems, okay? But anyways, so when it comes to scikit-learn, the main steps that you want to do to use machine learning are going to be as follows. The first thing is going to be to import the libraries. So you're going to be importing not just potentially scikit-learn, but anything else that you need to use as part of your program. Okay, you might need pandas or numpy or something to process like your data sets. After you do importing and kind of prepare, to prepare your system to run the algorithms and to store the data and the formats of the data, then you want to read in the data set that you have. And this data set doesn't have to be at this point pre-processed, or it could have been, because the next thing I'm going to write here is to do the pre-processing. This pre-processing can be anything from organizing the data set into a way that it's ready to be fed to a machine learning model, which is going to depend on what kind of format the model can take. So certain models take certain things, like, if you're doing classification versus regression versus clustering, you need different formats of the data. And so, in fact, when I think we will talk a little bit about like principal component analysis and reducing the dimensionality of data. Those are the kind of things you need to do before you can feed it to a certain algorithms, because otherwise it doesn't work. And so you need to do some kind of preprocessing there. But this preprocessing could also include like even the data cleanup part. The point is you gotta have everything ready to go to feed it to your machine learning model in the format that it expects. Now, how do you know what format it expects? Well, that's why we're going to be looking at these. I'm going to show you examples of what kind of data they expect, what kind of data they get, they expel once they do the machine learning model. So you can see what you need to do to actually make it work with your data set. But these things are really flexible, so don't be freaked out about trying to get things working. They're very, very flexible. At this point, now you have your data set and it's cleaned up and ready to go. You want to split your data set into either the 2 or the 3 categories that I just mentioned. So training, testing, and potentially validation. Okay, again, the validation is not really required unless you're actually going for like a publication thing. If this is something you're just doing for yourself, training and testing will do. But if it's something that you're trying to compare against like state of the art, you probably want to do some sort of validation. Now, there are ways around this, like for example, there's cross-validation. So what cross-validation is usually something like tenfold cross-validation. What that means is that you keep rotating what you feed versus what you test with. So you do something like feed 90% of the data as training and 10% as testing. And then you keep rotating that 10% around the entire data. So the first time, like, think about it, let's just say the first time I'm going to feed this piece as the training and this is the test. Then the next part, I'm going to feed this piece as test, and then this is training. And then the next part, I'm going to do this piece as test, and then this and this is training. And then this piece is test, and then this and this as training. So I keep rotating it around, and I test them all, and then I kind of take the average of all of them, and that becomes my overall accuracy. That would be what's known as tenfold cross-validation, because you keep flipping around 10%. That's another way of making sure that you don't just pick a really lucky testing data set, because that's the other thing that can happen. You train your data with some really cool data, but then you do your testing and it fails, so you're like, darn. So let me pick the easy ones and make that my test, and then put all the hard stuff on the training so it learns all the hard stuff, and then when it has an easy test, it does really good, and you're like, oh look, I got 100% accuracy on my thing. Yeah, but you fed it the easiest possible test data set subset of your data. So again, these things can happen intentionally, but also unintentionally. So you have to be careful about that too. Like, you might just get really lucky when you split your data set, and you have to be aware of that, because otherwise you look like a fool if you submit something that did good on your data set, but like literally fails on everything else. So after you do your splitting of the data set, then you go in and you feed it to the model. In other words, you make the predictions. Okay? Actually, no, we're going to consider this a different step. So you feed it to the model to train. Train, test, do all the stuff it's got to do. Just keep running until it's happy. Then, once you're happy with it, then you can make predictions with it. Okay? By that, I'm saying it comes a time to evaluate whether your algorithm did good or bad. So this is when you're doing your validation. Make predictions and compare. In other words, evaluate it. And that's it. That's all the steps. Of course, if you're just training it, then this itself is like a back and forth process. And then you have another evaluation, which is like your validation one. That could also be the case. If you already trained the model and you're really happy with it and you're going to feed it brand new data just because it already works, then you still do this stuff in the order of importing libraries, import data set, doing any pre-processing. You don't need to do any splitting anymore. You just go straight to actually making predictions and feeding it to your current model and evaluating those and analyzing the results. So it's only if you're training the data set for the first time and you're actually building your model. It's only if you're training your model that you actually do the whole train, test, split circles. Once you have a happy model that just works really good, then you don't need to train it anymore. You just let it run. Now you could have models that not only do they run, but every time they keep updating the training and adding more training to make it even better. But that's a different story. Okay, so that's kind of your thought process. Actually, not just for scikit-learn, but in general when you're using machine learning library, that's kind of the way that you're going to handle it. So let us go ahead and just really briefly look at scikit-learn's website. So this is scikit-learn's website here. And let me tell you a little bit about scikit-learn. So it was initially developed by, actually let me write this guy's name here. This person. Well, I mean, I believe it's a person, but it could be an organization. I don't know. Check on Wikipedia. I just have the name written down. But it was developed by Kornapu in 2007. But it took about 3 years to get like the first real release, like an actual practical usage of it. You know, because there's a difference between like, hey, I made this cool project and it works really nice, to like, okay, now I'm ready to like release this to the world and it's actually a well completed product. The library itself, scikit-learn, is part of a major, like a larger group of libraries, which are known as the Scientific Python. So actually, keep switching back and forth. The Scientific Python. In fact, that's where the name comes from, scikit, since I believe that scientific kits, maybe that's how they came up with it. But I know for a fact at least the sci part comes from Scientific Python, and it's part of the larger. And by the way, if you want to Google those are called Scipy, like that. And so the Scipy libraries group of libraries was basically made for data analysis and scientific computing, like math stuff and formulas and that kind of thing. And when they came up with the machine learning exclusive one, they just said, well, we're going to keep using the scikit part, but we're going to call it learn, just because machine learning, scikit-learn. So that's how the name came to be. It's a little fun story for you. And so here's the website, and it's amazing. In fact, you'll see me refer to it a lot as I go over a lot of these things in the next couple of videos, because they have amazing examples. And whenever you're trying to use any of these algorithms, all you gotta do is look at an example of an existing one and just copy paste that into your code and then start tweaking it until you get it working. And that's pretty much the way you run it, and that's okay. That's normal. So as you can see, they have different types of algorithms for machine learning. There's classifications, there's regressions, you have clustering. So I guess classifications, you can see the different classes of things being separated here with nearest neighbors. We will talk about a little bit of that at one of these lectures. Regressions is for lines, as you can see. It's like trying to predict the price of a stock given X amount of time or something. And then clustering is grouping things into different categories based on where they belong. So you're trying to just take what may look like a bunch of dots that are unrelated and trying to group them into as many categories as you want. And so k-means can be useful for that kind of process. And that one I don't know if we'll cover, but I do have the code for that. I did the code by scratch once because somebody made me do it. Maybe I'll find that. If I do, I'll share it, but I doubt it. It's been too long. Dimensionality reduction, that's the PCA that I was mentioning earlier. We might look a little bit about that, but probably not. There's just so many things that you can do in scikit-learn. They do have some pre-processing stuff. In fact, I could talk about normalization and I forgot the name of one really cool one. Maybe it'll show up if I click more. Let's see. I don't remember what it's called, but I know for a fact that I talked about it for quite a bit in my dissertation, which is kind of sad. The name is on the tip of my tongue. It's okay. Let me describe what it does, and then I'll remember. So when you have certain groups that you want to train on, so certain classes, and it's an unbalanced amount of them. So for example, suppose you're trying to make this algorithm that can classify things into triangles, circles, and squares. But like 90% of your training data set is just all triangles. Then you got 5% circles and 5% squares. When you're training it, your model is going to be biased, like just naturally, because like frankly, if I tell you like, yo, I'll give you $1 million if you guess whether I have a triangle, a square, or a circle, and I tell you that literally in your training of this, 90% of them are triangles, and then 5% are circles and 5% are squares. You don't even think about it. You're like, well, okay, it's going to be a triangle then, because like if 90% of them are triangles, I don't even need to look at the shape at all. I can just tell you it's probably a triangle because I have 90% odds of actually just getting that right off the bat. And so that's literally the same thing the model learns. If the model has a high amount of one class than the other ones, it's going to get naturally biased towards it. And it's a pain because while it would be nice to have a nice and even training data set where we have an even amount of each, unfortunately, that's not how the world works. So what do you do at that point? Well, one thing you can do is you can just chop the amount of triangles that you feed it. So you feed it a fair amount, but that means you just lost about 85% of your entire data set because they were all triangles. The other thing you can do is you can take the smaller ones, so you can take the 5% squares and try to use these, but slightly modify them so that they kind of appear as different data points when it's really just one data point. How do I do that? Well, if it's actually a drawing of a square, you could copy and paste it and then make a slight modification to it that may look the same to you, but there's like one pixel that's different. And by doing this hackery, essentially, you make the same amount of squares as triangles and as circles, and it actually helps a lot. Like it legitimately does. Like it unbiases. It might still be biased a bit because they're going to be very similar, but it'll be enough to help reduce this bias issue. And this whole thing has a name, and I think one of the algorithms for it is called A-design, now that I remember. So let me see if I can find that one on Google, because that'll tell me the time. And Smo, yeah, there's Smo's the other one. So, yep, so yeah, I knew that if I explained it, I would remember it. Imbalance learning, that's what it's called. Imbalance learning, yeah. Here's the name in case you're curious. Let me write it down for you. It's a really cool sort of approach to solving the bias problem of machine learning. I think there's part of scikit-learn, but now I'm actually trying to. Are they though? Let's see where other signs are implemented in. Yeah, there's a different website called Imbalance Learning. I think that they're part of the Scipy, but I don't know if they're part of scikit-learn. So, okay, fair enough. But yeah, and the two algorithms that I know is Smo and A-design, and what it's that synthetic generation of like extra points for a given class, that are a little bit more elegant than just trying to add randomly modify them. And I tried them out in my work, and they helped. I didn't have an extremely unbalanced system, but it was still somewhat unbalanced, as naturally as things are. And I think I increased my accuracy when I was trying to do predictions by using it. So it worked out for me. It might work out for you. It might not, but it's always worth trying. That's one of the things you do. But anyways, that's amongst the things that you would want to do to pre-process data, is you would want to balance your classes. And that would be a fair thing to do. But in this case, there's other things here, such as feature extractions. So you may not, a feature for a model is something quantifiable usually. Not everything is quantifiable in life, so you have to find a way of making it quantifiable. So that's going to be some of the feature extraction that you could end up doing. So yeah, that's essentially what your scikit-learn library is and what it can do. For each of these, what you'll find is, like if I click on SPMs, for example, you're going to find an explanation of what an SPM is, what it's good for, what it's not good for. So it's going to have advantages of something, disadvantages of something. It's going to explain the different kinds of SPMs that you can use, in this case for classification problems, and it's probably the SPRs for regressions. Yeah, so regressions, you got support vector regression versus support vector machine. These are in a future video I'll have posted when we get there. But yeah, so you'll have the different models within this. So support vector machines, to recap it quickly, is a type of algorithm that is for machine learning. And so this is using that type of machine learning for different kinds of problems, whether they're classification or regression problems or clustering problems even. And so what it's going to do is it's going to explain to you the different subtypes. So within support vector machines, there's something known as kernels, and there's different kinds of kernels. And each of those give you different results. And here they got some pretty graphs actually to kind of explain that. But yeah, so they're trying to give you the basic sort of foundation so that you can understand what the algorithm is. And then they give you the code, like as an example of how to use it. And as you'll see, some of these blocks are really small because you don't need a lot of code to run these models. In fact, that's what's so powerful about libraries like scikit-learn. You can run these models that are based on some serious hardcore math and a lot of work, optimization that went into them, and also just work in general. And you can run them with 4 or 5 lines of code. So it's an incredible thing. And it's really a shame that not that many people use them. So when so much power is available at your hands. Unbalanced problems. I wonder if they talk about A-design and Smo in here. But maybe not. So yeah, this will all depend on the different categories here. You'll see it at the left as sort of a table of contents, and it'll vary depending on what you do. You got some nice math if you want to see the math behind something like an SVM, and some references so you can further educate yourself on this specific machine learning model. But the important thing and what you care about is this stuff. Look how many lines of code there are to run this. I know we haven't looked at SVMs, but like you still understand what this is doing. If you think back to what I said here, the steps here: import the library, import the data set, do your pre-processing, split the data set into training and testing, run it on the model to train the model, test the model on a specific new value to evaluate it. That's what you're doing here. From scikit-learn, which is the name of the library, scikit-learn, which you have it in Python, import SVM. So you're importing the SVM model from it. Okay, that's step one. Step two is import a data set. In this case, rather than importing data set, they're just making it themselves. They got X and Y values. Think of this like an X and Y graph, y equals mx plus b, or y equals ax plus b. That's your X is like your input and Y is your output, right? So this is saying like, if we feed it 0, 0, I should get a 0 back. If I feed it 1, 1, I should get a 1 back. So 2 points, simple training for 2 points, but it could be a billion points if you wanted. 1 billion points, it'll be the same. Then you take that information and then you are going to feed it into your model to train it. This line of code is creating the model, the type of model. So it's like storing into a variable the type of support vector machine you're trying to use here, which in this case is the SVC, which support vector clustering maybe, or what does SVC actually stand for? Classification. So you load the type of model you're about to use, and then you run it with fit. And what that's going to do is that's going to train the model based on its input, on its training input here. Okay, so I guess this is one extra line of code that is not in the instructions there, but you can kind of combine these two. Technically speaking, I could put svm.svc.fit, but the thing is that the model, once it's finished, it's going to be saved into CLF. So that's why they're making the variable first, so that it gets saved somewhere. Okay. So basically, choose the model you want by this line, train the model with this line, and then once it's done, if you want to test your model, you test it with some new data. So you're gonna feed it this data of 2 and 2, and see what it basically gets you back. What this returns, which in this case it returned the 1. So that's what you got back from that. Which of course, it could only return 0 or 1 because that's what you fed it. So it's like, it probably trained itself to say only 0 is 0, and anything not 0 is probably 1. So that's my guess. Okay, but yeah, that's literally all there's to it. It's a very, very straightforward process to do these things. Let me re-zoom out. There we go. And then, which one do I want to see? Oh yeah. So I wanted to just very quickly show you this getting started, which shows another. Well, I kind of already went over time, but here's another example. Random forest trees, another machine learning model, pretty decent too. Here's your importing. Here's loading the model into that variable again. Here's your training data. Here's your actual training of the model by using fit function. And then here's you testing the model with the new piece of data. That's all there's to it. What is this? 1, 2. I'll consider this one line of code because you're just loading a database. 3, 4, and 5. There's 2 here because they're doing 2 predictions. Okay? It's not hard. What's hard is to understand the models. That's what's hard. So you gotta know which model to use in which situation. That's hard to know because you gotta understand them. But also you need to know some of the parameters. So you'll see that whenever you're running one of these, so if you actually go back to the support vector machine, in the documentation, they'll sometimes have a section with parameter details. So for example, here, let's just click on linear SBC. And so this is a specific one. Actually, here, let's do the one that they did. So SBC, just SBC. Okay? So this specific version of the support vector machine is for support vector classification, C support vector classification. The function has a bunch of parameters. Now these are the ones that you're going to have to read depending on which one you want to use. So like here you might be like, oh, what can I feed it? Well, the important thing for support vector machines in general is the kernel that I was mentioning. Again, when we talk about support vector machines, we'll talk about kernels, but you need to tell it which kernel you want to use. So there's an argument or a parameter within the function call that you see in the previous page. So here, right now, they're not really passing anything other than the default parameters, because you can see there's nothing in there. But you can pass in a ton of things. And so this is what's going to improve your model so it works better. And to understand which settings to tweak to improve it means you gotta really understand how the model works. You gotta understand how the math works. We're not gonna go to that extreme hardcore level on this class. You'd have to take a exclusive machine learning class for that. But you can at least educate yourself online about what would be the best settings for this, and it's just something you can Google too. For example, as basic as the kernel, linear, poly, RBF, sigma, pre-computed. If you're doing something with classification that is like binary classification, sigma will probably work out okay. But if you just want to, like, one of the kernels that just kind of works always, like, is RBF, is pretty decent. In fact, that's why that's the default. You can see here it says specifies the kernel types to be used in the algorithm. If none is given, RBF will be used. That's probably because it's the most fits all scenario, and that's the best usually. And that's the thing. That's the cool thing. Like, if you don't pass in the arguments, it'll pick what is usually the best case scenario. Like, it's like what the best cases are. RBF, because it's like the one that works most of the time. So you only need to start tweaking with the arguments once you kind of have a baseline that is good. And now you want to push it further. Then you start tweaking with the arguments. Unless, of course, you know the model by heart, and you can just go from point A. You can just start out tweaking things before you even run it once. So yeah, so you just basically read each of these and then understand what they do. If you don't understand it based on this, you can kind of Google that sort of idea. So like you can Google what the RBF kernel is, but even Wikipedia has a really good kernel page that explains that. But yeah, there's just tons and tons of arguments here that you can modify. You can see this is what it could look like. Kernel RB. In fact, well, this is probably the default ones, but this is what it can look like if you put a bunch of other arguments in there. It could be this massive function call. But that's just because you're customizing it. You're trying to make it work as the best you can for you, and that's a good thing that you can customize it. So that's the other part of scikit-learn that you want to do, is you want to kind of look at the specific function you want to use once you decide for an algorithm, then look at the arguments that it can do, and see how to modify it to make it work better for you. Okay. They do have an introduction to machine learning link, which I'm going to share with you. I please encourage you to actually read this now that you've seen the machine learning first video. So go into this and just read it on your own time. I encourage you to also play around with this iris data set. I may play around it when we do the linear stuff too, and maybe do something like this. But even if I do, I still want you to play around it before, so you can get a feel for what it's like to read the documentation, try something out, and go from there. Okay? So that's really all I have for you. It's a shorter video than normal, but I really just wanted to make sure that that I sort of gave you like a brief, like, hello, this is what scikit-learn is, so that you can start using it. And of course, if you want to know how to install it, there's on the top an install button here, and there's your pip install. So scikit-learn, no shock there on how to install that. So I don't know if I have it installed in the VM. If I don't, next video before I start doing something, I'll show you what it's like to install it. But yeah, it'll install pretty well, pretty quickly. You can read more there if you run into issues or you want to install it with a different way. But I like pip. It's just so nice and convenient. Makes life easy, so why not use it? You can see there, you can choose which OS you want, so you can see the instructions for that. I have Linux, so I do use the pip 3.1, so there's that. And the Conda is for like you're using that system, and for Windows primarily, I think that people use Conda. Yeah, like Spider and the Conda. But yeah. Okay then. So that's all I have. Until the next time. Thank you for watching, and get ready. This is where things get really fun with scikit-learn. We're gonna do some cool things. I know that you're gonna like it, so I'll catch you around on the next video. Until then, take care.